homotopy theory. Our first speaker today is Hana Jia Kong from the Institute for Advanced Study, and she will tell us about derived categories, triangulated categories, and T-structures.
Okay, thanks for introducing me. Yeah, so I will be talking about these three things today. And I will start with derived categories and triangulated categories in the classical setting, in the, ordinary categorical setting. So what is a derived category? We start with a abelian category, which I denoted as A. And if you have an abelian category, you can talk about the category of cochains in A. Cochains in A. And the objects, they're cochains and morphisms, cochain maps. So for example, an object is like this. So for cochains, usually we write the subscript, we write this the degree in the subscript and in the superscript, and the differential is decreasing. So like it's increasing, sorry. Okay. And then you can define, so morphisms are morphisms between cochains. And you can define cohomology of such an object. And also we have a notion of quasi-isomorphism. That is so a map between two cochains. It's a quasi-isomorphism if the induced map on cohomology is an isomorphism. So the quasi-isomorphisms, they're not equivalences in the category of cochain complexes, but we can formally invert all these morphisms. So we start from the category of cochain complexes, and then we localize the set of the collection of all the quasi-isomorphisms, and that gives us the derived category of A. So here, localize at these things, what I mean is you just formally invert all these quasi-isomorphisms, you add in some the wrong direction arrows of these quasi-isomorphisms, so that these quasi-isomorphisms, they are actually equivalences, and the result category is this thing called DA, and that's a derived category of A. Okay. All right, and so there are also some variations. You have cochain complexes, and you can talk about the bounded cochain complexes. So you have CH plus, CH minus, or CHB. And these are bounded from below, above, and from both sides. And you have these bounded things, and these bounded things, they also gives you the corresponding bounded derived category of A. And So why we care about derived categories? One reason is that we have something called derived functors. So for example, X, group cohomology, or XTOR, these are derived functors, and we want to start the derived functors, and the derived category gives you a framework to define or study these derived functors. We also have derived functors in the stable homotopy category. And actually, the stable homotopy category, its construction shares some similarity as this construction of derived category. It's also, you start with some category and formally invert several things. So let me write that down here. The stable homotopy category. So this is, we start with the category of spectrum, and then we localize stable weak equivalences, and we arrive at the stable homotopy category. And yeah, as mentioned before, this is there's something similar between this construction and also the construction of derived categories. And you can find, if you're familiar with these two things, you can find more things in similar. For example, in the derived categories, we have this shift functor, which is you shift the degree of a cochain complex. And in the stable homotopy category, we have a suspension functor, which is smashed with S1, the degree 1 sphere. And also in the derived category, we have exact sequences. In stable homotopy category, we have cold fiber sequences or fiber sequences. And all these things in that are similar, we can organize them into a structure called triangulated category. So the next topic is triangulated category. Triangulated categories. What is a triangulated category, and why that's useful? So in this talk, I will abbreviate this using notion a triangle and then CAD. That's easier to write down. So the triangulated category, it is a tool. It is a tool to help us to describe the structure inherent in things like the derived category of some abelian category or the stable homotopy category. And the definition is, I'll talk about it right now. So we first fix the notation D, and this is the additive category. And an additive category, the definition is it's a category that is enriched over the category of abelian groups. And first, if we have an additive category, then we can talk about what is called the shift functor, or sometimes this is also called the translation functor. So a translation or shift functor, it is a functor on D to itself. And usually we use the notation bracket 1 or suspension or sigma. So these are the most commonly used notations. It is a functor from D to itself, and it is an additive automorphism. So it's an equivalence and it's an additive functor. And we also need to talk about triangles, distinguished triangles. Or exact triangles in this additive category D. So a distinguished triangle is something that consists of the following data. You have objects X, Y, Z, and you have map X to Y called F, Y to Z called G, and Z to the shift or the translation of X. So I'll use this notation suspension and this map FGH. And so such data is called a distinguished triangle in the category D. And now we can define what is a triangulated category. Okay, so a triangulated category consists of, first, you need an additive category D, and this D is equipped with a translation, a shift functor sigma. And also you need to specify a class of distinguished, or let me say exact triangles in D. And 1 and 2, these data, they need to satisfy the following axioms. And let me write down these axioms. So move that down a bit. So we have 4 axioms. The first axiom, there are 3 subparts. So the first part, it's about triangle involving identity map. So the identity map together with the zero map, this is a triangle. And also something about completing a triangle. That is to say, if I have any map from X to Y, then there exists an object Z fitting to a triangle such that this first map is F. Oh, sorry. I want to use this notation. Okay, and also the third thing is it's triangles closed, they're closed under taking isomorphisms. And that is, if you have two triangle, you have a triangle and you have another sequence of maps, and you have an isomorphism between these two sequences, then the other thing is also a triangle. That's the first axiom. Okay, And the second axiom, it's about, let me call it rotation. So it says that if I have a triangle, X, Y, Z, to the suspension of GH, if I have such a triangle, then you rotate it, you also get triangles. So Y to Z, Z to suspension of X, and suspension of X via suspension F to suspension of Y. This is a triangle, and if you rotate back, then you get X to Y to Z, and this is the -1 suspension of Z, and this is the -1 suspension of H, F, G. Then these two sequences, they are also distinguished triangles. Okay, so it's about you have a triangle and then you rotate it, you also get triangles. And the third axiom, I'm hoping, oh, never mind. The third axiom, it's about functoriality. And let me call it weak functoriality. Let me first draw a diagram. I have a distinguished triangle X to Y to Z to suspension X. And also another one, X prime to Y prime to Z prime to suspension X prime. And I have map U and V here. And this is suspension of U. And suppose this map commute. So let me write down the assumption. So the axiom assumption is that we have this and this are triangles, and the square commute. Oh, wrong color. Then the axiom conclusion is that we can find an error here such that everything commute. Okay. Right, and this axiom only says that such a map exists, and it doesn't say anything about the uniqueness, and that's why it's called weak functoriality. I will come back to this. I will come back to this axiom later. And also this fourth one involves a large diagram. It's called octahedral axiom. And it says that if we have, let me again write down a diagram first. Z prime is X, Y, Z. Okay, and here I assume this, and this, they're distinguished triangles. Let me number them 1, 2, 3. And I can look at the other sequence, try number as 4. So the axiom says that if 1, 2, 3 are triangles, and also everything in this diagram commute. Then we have add this here. Then we have then we have this 4 being a and it is a triangle, and everything commute. Okay. Right. So we have these 4 axioms most commonly used to describe the definition, to talk about the definition of a triangulated category, and there are some variations of these things. And these 4 axioms, they're actually not independent. For example, the third axiom, this weak functoriality axiom, it can be deduced from others by some results by Peter May. But it's useful to, well, it's helpful to describe the definition of triangulated categories using these axioms. And yeah, I mentioned that this is weak functoriality, and there's some subtlety about this third axiom. Before we talk about that, maybe let's first see what examples we have. So example of triangulated categories. Actually, I have mentioned it at the beginning as an intuition. We have the derived category of some abelian categories, and also the bounded version, and also the stable homotopy category. These are the most the intuitions behind this definition of infinity-category, triangulated category. And in the derived categories, the shift functor is the shift, and in the stable homotopy category, the shift functor is suspend with sphere S1, and you have exact sequence. Triangles are the exact sequences, and triangles here is co-fiber or fiber sequence. So this is also why you need the stable homotopy category, not only the homotopy category. So for stable homotopy category, you have co-fiber sequences equals fiber sequences, and this is not necessarily true in the unstable homotopy category. And also because in the axioms, in the definition, you need that the suspension functor, the shift functor is an automorphism, and that means you can desuspend, and that's not true in the homotopy in the unstable homotopy category. Okay. Yeah, and if you have a triangulated category, then some properties or exercises properties you can immediately deduce from the definitions from these axioms. For example, you have if you have a distinguished triangle, then the composition, the composite of successive maps are 0. Okay, if this is a triangle. And also you have that if I take the home functor, then this takes a triangle to a line exact sequence. So some fun exercises. You can try to use the axiom to prove these properties, and also you can also try using 2. You can prove that in the second axiom, V is unique. So the second axiom is a completion. Is that the second? Oh, sorry. The second part of the first axiom. I mean the third axiom. Let's see. Oh, I'm sorry. The second part of the the second part of the first axiom. And it is unique up to isomorphism. And something I want to mention here is that maybe a warning. D is unique up to isomorphism, but up to not necessarily unique up to not necessarily unique isomorphism. So that means you have Z and Z is unique, but unique up to isomorphism, but the isomorphism you can choose. You have choices of these isomorphisms. Or another way is if you look at TR3, then the arrow is not unique. Maybe it's best if I copy paste this picture and put that as a reference here. So in TR3, this you have this and this, and some map to fill in here to make everything commute. The choice, you have some choices. This is not a uniquely determined map. So a counterexample would be if I look at A to 0 to suspension of A to suspension of A, and oh no, this is 0. Okay, I have the upside and downside. The upstairs, downstairs, you have 2 triangles, and of course this is commutative, but you can take any map here to make everything commute. So this is an example showing you that in the third axiom, this vertical map W is not necessarily unique. And this is why it's called weak functoriality. You don't have this uniqueness. And this is something bad about triangulated category. So it's mentioned yesterday that if you look at a stable infinity category, then you can take its homotopy category, and its homotopy category is a triangulated category. And this weak functoriality is it's sort of fixed in the stable infinity categorical setting. So if I have a stable infinity category D, we talked about yesterday. We talked about it yesterday that the homotopy category is a triangulated category. And also, in the stable infinity category, well, in the homotopy category, the shift is given, the shift functor is given by, or the completion of triangle is given by taking cofiber. The distinguished triangles, they are cofiber or fiber sequences. And the cofiber sequence construction remember that's defined by you take the push out of a square, and that is essentially unique. So the meaning of essentially unique is that it's unique up to some choice of contractible spaces. Or when you say unique, you can talk about unique up to isomorphism, or unique up to not unique isomorphism, but the choice of isomorphisms, they're unique up to some isomorphism between these isomorphisms. And so there are all these levels of homotopy hierarchy, and essentially unique basically is saying that you have uniqueness if you consider all the uniqueness in higher homotopies. Okay. So that is about the derived category and triangulated category in the classical setting. And we also have derived category defined in the higher categorical setting. So the second part, derived categories in the higher categorical setting. And the reference for this is Lurie's. I'm using Lurie's higher algebra. And this things are in section 1.3. So the derived category of an abelian category in the high categorical setting is that you take some, it also starts with an abelian category. And you want to build a category which in high algebra is denoted by D minus A. This is a bounded. Maybe let me say the infinity category of derived category of A. And roughly, this is the following. So the objects, they are the projectives. Projective objects. The projective and right bounded chain complex. And the one morphisms are maps of chain complex. And the two morphisms are chain homotopies, and so on and so forth. Okay, and maybe, yeah, something I want to say here is the chronological and homological convention. So in the classical setting, it's defined using cochains, and cochains, and in Lurie setting, it's using chain complexes. So there is some translation between right bounded, left bounded, bounded from above, bounded from right, from below. And I find the best way to do it is that if you always write your arrows to the right, then so for example, in the cohomology convention, if you write arrows to the right, then it's increasing. And in the homological setting, it's decreasing. So when you say bounded from right in the cohomological setting, it's everything in everything vanishes in very small degrees. And in the homological setting, that's everything vanishes in very large degrees. And if you add the negative sign to translate between cohomological and homological, you see that there's no ambiguity when you say right bounded. But there will be some ambiguity if you say bounded from above or from below. And so in Lurie's convention, it says right bounded and using chain complexes. That means you bounded from here. That means in the chain, in the homological convention, it's bounded from below. And if you translate it to cohomology, then that's bounded from above. Okay. The cohomological and homological conventions, these superscripts, they're very, very confusing, I have to say. Okay, and I don't know if I have time to talk about let me maybe quickly sketch how Lurie constructed this derived category, this D minus of A. So sketch construction. You start with A, and then you look at the full subcategory spanned by the projective objects. And then you can take the right bounded chain complexes, right bounded. And you can make it enriched over the chain complex of abelian groups, and then use a functor. So the first step is truncation, and then you use the dot-Hahn correspondence. So this is equivalent to simplicial abelian groups, and then the forgetful functor, and you get to the simplicial set. So you can apply this functor to the morphism object-wise, and then you can view this as something enriched over simple set, and then you take the coherent nerve. So there is a functor from simplicial category to simplicial set, and this brings to the derived category. So basically this is a construction, and actually in Lurie it's not, it's using another, this is defined using another equivalent functor. So in Lurie, he construct a functor such that you can go directly from here to here, and that is called, his notation is NDG, a differential graded nerve, and the resultant category, infinity category, is equivalent to what you get from the construction here. Yeah, this is a homotopy coherent nerve functor. So there's a question in chat, is this homotopy coherent nerve functor? And the answer is yes. What I just said in HA, it's another construction. DG by equivalent. Okay, and properties. So I just mentioned several things without proving anything. So this is, if you take this derived category, this is an infinity category, and you look at its homotopy category, then this coincide with a classical bounded classical derived category. This is what, well, if the construction gives you a correct thing, then you should, this is something that's expected. And also, of course, it is a stable category, the stable infinity category. And for a stable infinity category, we can talk about, actually, for a triangulated category, we can talk about the T structure on it. So the third topic, T structure on triangulated categories. Yeah, so definition. T structure, a T structure, I forgot. Let me first fix D, which is a triangulated category. And the T structure on D consists of, so a pair of 4 subcategories. D greater or equal to 0 and D smaller than equal to 0, and these are closed under taking isomorphism. By the way, here I'm using the homological convention. If you check the Wikipedia page, then I believe Wikipedia page is using the homological convention, and everything is a superscript, and there's some symmetry you need to translate between these two conventions. And the second thing is that the greater or equal to 0 part is closed under taking suspension, and the smaller equal to 0 part is closed under taking desuspension or detranslation. And we have that for anything in the greater or equal to 0 part, anything in the smaller or equal to 0 part, if you look at the map between them, between x and the disuspend of y, then that's always 0. And the fourth condition is that for any object in D, there exists a triangle x to z to y such that x is in D greater or equal to 0 and y is in D suspend of D smaller or equal to 0. Okay, so these are the axioms for T structure. And maybe some notation. Some notations, see. When write D greater or equal to 0 for the nth suspension, nth shift of D greater or equal to n. Sorry. We write D greater or equal to n for the nth suspension of D greater or equal to 0 and D small or equal to n for the nth suspension of negative n. Okay, and also we write D heart. This is called the heart of a T structure, and this is the intersection of D greater or equal to 0 and small or equal to 0. And examples. So the most common example of triangulated category is the derived category and the stable homotopy category. And we look at the most common T structures on them. So for the derived category, we can define the greater or equal to 0 part to be everything whose homology, or well, here it should be homology, concentrate in the greater or equal to 0 part, and similarly for the small equal to 0 definition. And this defines a T structure, and it's not hard to see that the heart of this T structure is a category of abelian groups. And for the stable homotopy category, we can look at what is called the Postnikov T structure. That is, the greater or equal to 0 part is everything whose homotopy groups is concentrated in the greater or equal to 0 part, and similarly for the other small equal to 0 part. And if you think about what is in the heart, then that is things whose homotopy groups concentrates in degree 0. So that's Allenberg-MacLean spectrum. Therefore, the heart of the stable homotopy category is equivalent to the subcategory consists of the Allenberg-MacLean spectrum, and that's abelian groups. So the derived category and the stable homotopy category, yeah, I should have right Z here. Otherwise, this would be A. Oh, let me just change to A. Okay. Yeah, if I take A to B abelian groups, then you can see that the derived category of abelian groups and the Postnikov T structure of the stable homotopy category, they have the same heart. There are also something called the truncation functor, which you can talk about if your triangulated category is equipped with a T structure. So the truncation functor, I think this might be an example that will be mentioned in the later talk, in Bus field localization talk. Maybe the truncation functor is I just say that this is a colocalization with respect to e greater or equal to 0 n, and we can also consider the localization with respect to this more equal to n subcategory. And this colocalization, localization, it's defined, it will be talked about in later talks, and it's defined using universal property. One way to define it is to using universal property. And maybe it's easier to understand if I use examples. So in example 2, this gives the n's connective cover. This is the n's connective cover functor, and this is the n's co-connective cover functor. And an application of truncation functor is set and get filtered objects. Oh, an extra arrow. And you can use it to define spectral sequences. Again, in example 2, this is the I always choose the wrong color. Gives a Plasnikov tower. Okay. So in the last few minutes, yeah. So let me talk about the T structure in the Infinity-Categorical setting. So the T structure here is defined triangulated categories, and you can also in the stable infinity. So T structure on a stable infinity category is defined by passing to the homotopy category, because the homotopy category of a stable infinity category is triangulated. So you can define T structures on the homotopy category, and the T structure on the stable infinity category is defined by passing to that. And so when just seeing the category, the derived category, the infinity category of the derived category of A. So T structure on this thing is defined in this example. Oops. Well, in this example, that is, we have mentioned that the homotopy category of this is a classical bonded derived category. So we just take this definition, and that gives you a T structure on the infinity category of the derived category of A. Yeah. And as expected, if you take the nerve, if you take the heart of this T structure, then that would be the infinity category associated to the abelian category A. Okay, and yeah, let me state this universal. I want to state two more results. Universal property. So one is universal property of the derived category. And this is, you can compare this to the classical theorem, which we have when we talk about derived functors. So A is, say, abelian category with enough projective objects, and the C is a stable infinity category with a T structure, and here we want this T structure to be left complete. So this means nothing in C greater or equal to infinity. There's no positive, infinitely positive object, or you only have the zero object there. And so we look at the functor, the subcategory of the functor category from the derived category to C, derived category of A to C. This is a fourth subcategory spanned by functors that preserve greater or equal to 0 part. So they also have a name, right? T exact functors. These are things preserve greater or equal to 0 part. And you also require that these functors, well, this four subcategories consists of these functors that are right T exact and sense projective in A to heart of C. Then the conclusion is, it seems a lot, but I will explain what this means. It says that this four subcategory of functor category is equivalent to the right exact functors from A to heart of C. So right exact functors means you preserve finite colimits, and this equivalence is given by, you first look at your functor F, restrict to A, and then you take the truncation small or equal to 0 to make it a functor between these two categories. And the way to interpret this is you should compare this to the classical result. That is, if we have a left exact between two abelian categories, Then and A has enough injectives. Let's see, I use right exact here, so let me change everything. Right exact, it has enough projectives, then you can define the derived functor. The bad at left and right. I think that it's a left derived functor of f from the derived between the derived categories, and left derived functor. Okay, yeah. So this universal property of derived categories, you see that under all these conditions, which compare parallelly to this result, to things in the classical setting, you have an equivalence between these two categories. So that's saying that once you have a right exact functor between the heart, between the heart that's to a abelian category, then you can extend it to a category between the derived categories. And that's exactly what this classical result about derived functor is saying. Okay, I'll stop here. Sorry for going over time.